Okay, so I'm going to start back up with lecture number 2 because our 10-minute break is over with. And we're going to go until 45 minutes from now. And so I'm going to cover, believe it or not, everything I need to do in lecture number 2. And then when we come back from lunch, we'll be doing our first exercise. So that's kind of the game plan. And for those of you who came in late, lunch is going to be 2 hours today. So we're going to come back at 2 o'clock from when I leave at 12. So, because I have to be, I'm doing a double play today. I have to be in 2 places at once. So, I'm going to my other place for 2 hours. So, okay, so last time, first lecture we went over, and this was the example we just left with. So I don't really need to refresh your memories on this. Hopefully you remember. We went through an example of mapping out a car that can navigate itself around a track and find objects and determine where it's going to go. And here's a picture of that car. And what did we do with this car? Well, we put together a prototype of the environment, and what I was doing was sort of setting the stage for how we're going to put together a problem solution to an AI challenge. And one of the things that you end up having to do is put together a prototype, and your prototype is going to be able to hopefully test certain environmental information and determine what's going on and kind of set the game plan in terms of your evaluation. And we looked at the major issues that were associated with that. This is a review of what we just covered a few minutes ago and how we're going to attack the problem. And we had the general architecture that we came up with, and then we had the anthology that we kind of looked at and kind of went, okay, well this is one for the football. And it's a map of the problem solution for the most part. So most of your solutions are going to have some sort of a map associated with them. It's going to be like a translation or a road map, if you want to think of it that way. Here's another one for the task relevant map, as I talked about before. And the interesting thing is that we have this thing called the agent. So this lecture is about the agent concept, the different types of agents, and how we're defining the agent. So the agent in this context, how it relates to the previous example, is it's the brains of the operation. So an agent is acting for the human to make the decisions given the environmental information as the inputs, the perceptions, or percepts in terms of the input, it's doing the processing, and it's coming back out with an action. The action's the output, and the action is going to be associated with a lookup table or metrics or something that's going to tell us, if this happens, do this. If that happens, do this, which is how the human actually sort of thinks. If you sit down and it's wet, you're going to stand up because, oh, I'm sitting down on something wet. Or if you touch something that's hot, you're going to back away. So it's kind of a reflex model for the most part. So we have different types of agents that are associated with the concept. And let's just get to the agent part. I'm going to kind of skip ahead this beginning of this particular and come to this point, which is slide number 15, because there's a little bit of repeat in here. So because I just gave you this lecture, now it's the next week. Because we're doing like the entire 15 weeks in one weekend. So we're now in week number 2. So we're going to look at in terms of the concepts. And the first thing we're going to look at today is what is an intelligent agent. So it's an overused term, overloaded, overused, and often misunderstood, and it's a misused term. It's not misused in terms of an intelligent search agent. People call them search engines, but they really came out as search agents, is what everybody uses for the internet, actually, to search items. It's a form of an agent. It's an information agent, actually. So anything that can be viewed as perceiving its environment through its sensors and then acting upon the environment through its effectors to maximize progress towards its goal is called an agent. So you have to basically have input, processing, and output, and then you're serving as an agent in terms of the concept. So one of the assignments is going to have you define an agent, and the agent definition is right here on page 16 of lecture number 2, is where you're going to find the information for that, which is going to be the exercise you're going to do after lunch. So for those people who came back and are sitting here right now, you know that this is where you're going to find the answers to everything in that particular exercise that you're going to do. We have this abbreviation called PAGE. PAGE is Percepts, Actions, Goals, and Environment. In mapping out the solution to the AI problem, we use a PAGE format. So this is going to be the formula for what you're going to apply for a solution. And PAGE, the P stands for percepts, which are the inputs, the actions or the outputs. The goal is why we're doing this. It's because we want to solve this problem. It's usually the problem. And the environment is, what are the factors we have to consider? And there's a way of mapping out the environment, there's a way of mapping out the goals, the actions, and the precepts, actually. And this formulates the solution that you're going to come up with. So we have task-specific and specialized particular types of environment. So well-defined goals and environments themselves are considered task-specific and specialized. If it's not task-specific, we have no idea what we're solving. And we have to specialize because we're going to come up with a way of doing it. And we're going to essentially refine it and make sure we're not doing anything else, but we're just going to solve that particular goal. So the notion of the agent is meant to be a tool for analyzing systems, not as an absolute characterization that divides out the world into agents and non-agents. So you can't take the entire agent concept and apply it to the general world and put everybody as an agent or a not an agent. We have agents. In fact, in our normal day-to-day life, we deal with a lot of agents. And we don't even think about it until you actually start defining an agent. And I'm going to go through some of those agents in a few minutes here. But agents, in terms of the intelligence in the artificial environment, that are human minds as networks, if you think of the concept, and thousands and millions of agents working in parallel. So in our human mind, we have an agent. If you wanted to take the human brain, divide it out per agent, which you can't normally do with everything, and you can't normally do it with a human either. I have an agent that tells me when I have to go to the bathroom. I have an agent that tells me when I'm hungry for biological functions. I have an agent that tells me when I'm tired. I have an agent that tells me when I'm bored. I have an agent. The concept of the agent, just dissect it out per activity or per function or per perception. I have an agent that tells me when it's dark, when it's light. So that's how you define an agent. So you can take a system and divide it out per agent and call them components, call them functions, call them behaviors, and then agent information is what you're designing. So an agent-based solution to an AI problem is the definition of the individual agents and then the controller that's making the agents all work together in terms of the concept. So to produce real-life artificial intelligence, the school holds that we build computer systems that can contain many different agents and systems for arbitrarily among the agents competing against the results. So our agents have to work when they have to. If you think about the operating system of a computer, it's agent-based as well. We have an agent that prints stuff for us. We have an agent that shows us stuff on the screen. We have an agent that takes our input. We have a bunch of different types of definitions there. So what we have is distributed decision-making and control that's going on. So the main brains of the operation is the map that's orchestrating the agent behavior from agent to agent in the scenario. So challenges might be in terms of the action selection, what next action to choose, which agent's going to work. And those are the decisions we make as humans. So if I'm sitting in the class right now, actually we just had a break, so nobody probably has to go to the bathroom, but prior to the break, your agent controller was going, well, I really have to go to the bathroom. But I think she's going to be done blabbling for a few minutes longer. Okay, she's going to be done soon. I'm going to wait. So your controller said, wait, because I think she's almost done. And then your agent said, okay, now we can go. So we can go. So it's a controller. The same thing that says, I feel hungry, but are you going to eat right now or are you going to wait another 45 minutes? You're going to have lunch. So you're going to wait. Children have to develop the agent. And that's what the parents do. The parent teaches the child how to organize the agents, which is because in a free will economy, and you notice this with kids all the time because you see them screaming throughout restaurants, you're not supposed to do that. Well, that's what the map is supposed to say, but they don't know that yet, so they learn the agent systems, and they learn how to control the agents, and then eventually they become adults and they still act badly. They still do things that are wrong, but that's the controlling or the controller. So we have sensors that come in, we have the agents that manage each one of the sensors, and then we have the effectors or the outcome, so which gives us our behaviors or our actions, and then we have conflict resolution. It says, I really want to tell her to shut up, but I can't. So the other agent says, okay, be nice, do this, okay? And then, you have to kind of sort of go through all the different agents that are in your head. Agent types. So we can split agent research into two main strands that have existed. We have distributed artificial intelligence agents, multi-agent systems, from the beginning, from the 1980s to 1990s, and then from the 1990s to the present day, the much more broader notion of the agent. We have the interface, the reactive, the mobile, and the information agents that come out. So I've told you one already that you guys have all used. The information retrieval agent, aka the search engine, is a classic example of an intelligent agent because it goes out and it tells you what information it can find for all of the things that you have requested. And Siri is kind of a natural language intelligent agent that works in the information retrieval mode as well. So now you can leave after this morning session and know what Siri actually is. She's an information retrieval agent. So that's all she is. That does natural language processing. So she's artificially intelligent. She's not that smart though. She's information retrieval. If the information's not in there, she doesn't know about it. So, although she learns though, huh?
There's something like lie detector, like when you're, that is also artificial intelligence.
Is a lie detector an artificial intelligence system? No. You know why? Because if you've seen the printouts of most lie detectors, it detects spikes in neurological paths that are supposed to, from electrodes that are hooked up. And it can tell connections that are being made. So it knows when you're thinking and when you're not thinking. And it knows when you've changed certain characteristics about your biological emotions. It's sensing emotions, it's sensing thinking, patterns in thinking. And it's a pattern match. So once you get the printout, the human has to look at it and say, oh, you're lying or you're not lying. There's stuff on it that says what's wrong. You can see the patterns. But it's the human that looks at that and analyzes it. If the computer analyzed it and looked at it, that would be artificially intelligent. But we don't have anything because it's judged. Because some of them come back inconclusive. They go, well, we can't tell. Because this person is extremely unemotional and doesn't express emotions. Or this person is a heavy thinker, and every time we asked them what their name was, they had to think about it. They had to go back, what is my name? Oh my God, and so their sensors don't connect correctly. Usually means they're guilty. No, I'm just kidding. It doesn't really, it has to be analyzed by a human. So, which is kind of interesting. But they have other, in fact, that's another area that's showing a lot of interest right now for doctoral students in artificial intelligence is biomedical equipment that's artificially intelligent. So it can take and analyze over, let's say, a course of a couple of hours, heart rhythm and stuff, and tell you exactly what's wrong. Instead of a human having to look at this, let's get the results back, let's run this test, let's run that test. It just takes and combines all the tests together to say the likelihood of something occurring is here. This is what it is, that's what it is. A lot of artificially intelligent research is going on right now to actually develop that. So I haven't seen anything on the lie detector, but it wouldn't surprise me if someone doesn't have it automated into an artificial. But the traditional lie detector test just gives you a printout. It's a test. So it's kind of like when you take a test in a class. So printout, it's like, it's not going to tell me whether you're going to pass the class or not, because you have to combine that with other information. So, all right, so I'm going to kind of skip ahead a little bit here and go talk about the windshield wiper agent. So what I'm going to just do right now is describe a solution to a problem, and the problem is how do you develop windshield wipers that work automatically? And it's an artificially intelligent solution because we're looking at, in terms of the solution, we're looking at these particular criteria. And the question I'm going to say is how do we design an agent that can wipe the windshields when needed? So that's our problem. So what I'm going to do for you probably in a couple of the exercises, probably not until the next class meeting, is give you something like this and say, how do we design an agent that can wipe the windshields when needed? Or how about, but yet, how do we design a vacuum cleaner that can pick up dirt from the floor? Or how can we design a car that stops automatically when it's supposed to or something? I don't know, some kind of, this is a typical problem solution. So the first thing we do is we look at, and this is the goals. The goal, the percepts, the sensors, the effectors, the actions, and then the environments. And one of your homework assignments, actually homework assignment number 1, is going to have you go through this process. So this is where you're going to get slide number 20, lecture number 2, the information for homework assignment number 1. If you're taking any notes, this is where it's coming from. So what do we have here? We have to define the goal. The goal is to keep the windshield wipers clean and maintain good visibility. All right. The percepts. Well, what are we going to sense from our environment? And perceptions kind of think of as in inputs. The inputs are going to be raining and dirty. If it's raining, if it's dirty, we're going to need to put the windshield wipers on. Because remember, you can put the windshield wipers on without it being raining. And the little water splashes up, cleans the windows. Sensors. Well, right now we're going to use a camera, maybe a moisturizer sensor, maybe, to solve this problem. Effectors, which is going to be the actions or the output. What effect is it going to have on its environment? Well, we're going to turn the wipers on. So we have wipers. They're going to be left, right, and back. So that's good, left, right, and back. And maybe the back of the car. And then actions, maybe on, off, slow, medium, fast. And then the environment, well, the inner city might be environment, freeways, highways, weather. So we can take the environmental conditions under consideration. If we sense rain, as an example, we have a moisture sensor or temperature sensor on our windshield, which is what most of them are doing right now anyway. Senses the moisture, puts them on automatically for you, but it puts them on slow. And then the higher the degree precipitation that it senses, the faster the windshield wipers go. Which is kind of interesting because on a foggy day, the windshield wipers come on. When it's not really raining, it's just foggy. So, and then you can turn it off and say, I don't like those auto wipers anymore. My windshield wipers are going off too much. So here's towards an autonomous vehicle here, in terms of our example. If we were to take this here, and I'm going to, there we go, move ahead to this filling in the blanks, because the first part of the slide set has all these question marks. What are we going to do? What are we going to think about? Well, I'm going to skip ahead and give you the answers. If I were to find other agent behaviors, and these are two more examples. So we have the one I just gave you a few minutes ago was on the windshield wipers. And now I have two more. One of them is going to be on a collision avoidance agent. And the other one below it is going to be on a lane keeping agent. So it keeps the car in a lane. In fact, we have these actually applied towards some of the newer vehicles that are out there. We have collision avoidance, you know, like when you back up and it goes beep, 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 like you're going to hit something. Or also there's sensors right now that tell you if you're not in the center of the lane. But how are they going to do that? Well, it has to read the ground. What if the camera's dirty? What if the lane's dirty? What if the line's not painted clearly? So it could make mistakes in terms of that concept. So just to briefly go through the collision avoidance example, if I were to say, how are you going to avoid collisions? Well, okay, so the goal, avoid running into obstacles. All right? Percepts, obstacles, distances, philosophy, trajectory. Everything's coming at me. How am I going to avoid that, or am I going towards that? Sensors might be vision, proximity sensing, which is going to be how you're going to avoid the curb. Actually, you're going to avoid hitting things. It's going to make a loud noise. Effectors, the output's going to be steering wheel, accelerator, brakes, horn, lights. It's things that might be affected by the condition as we get closer. The actions might be steering, speed up, brake, blow the horn, signal for the headlights or something. Environment, well, we're going to take and just consider the freeway in this particular example. If this was supposed to be for parking, it wouldn't be. It would be city streets or parking lot or location of the parking lot. For the lane keeping agents, we're looking at staying in the current lane and the lane center, lane boundaries, the vision, steering wheel, accelerator, brakes, steering, speed up, brake, freeway. So I'm going through this stuff because this is what you need to do for the assignment. Because I'm going to ask you something like this, and it's going to say, how would you design an agent that can wipe the windshields when needed? Well, that's how you would design one. These are the information that you need to put into the design. It's just a roadmap, and it's just one way of solving the problem, essentially. It's coming up with the information that you would need for it. So then you have to worry about another component called conflict resolution by agent selection and agents. And you have to define the agents, because this is giving us our individual agents. So after we define the agents, another good thing to do would be to create the controller of the agents, or the thinking mind. So we have an override. So the collision avoidance, what's it say? The collision avoidance agent and the lane keeping agent. Well, the collision avoidance is going to override the lane keeping agent, because if we put both of these two agents in a car, and the idea was to avoid a collision, well, we might have to get out of our lane. So, which is what we do naturally. When we're going to run into a car, most people would think about moving over left or right, get out of the lane if they can't stop fast enough. So that's how the logic of the controller is going to work. And an arbitrator, so if the obstacle is close, then this one. If not, then that one. So if it's close, then avoid it. If not, then change the lane. Worry about the lane keeping. And then a compromise, choosing an action that satisfies both the agents, and then any combination of the above. And then we have challenges, and the challenge is going to be, in this particular case, doing the right thing. Another challenge in this particular example, which is not on here, might be keeping people safe, or saving lives might be the challenge. Because there's so many different things that we could do, but what's the goal in terms of the, what kind of challenges are we going to come up with? Well, it's doing the right thing, whatever makes sense logically in this particular case. So the right thing means that we're creating a rational agent. So I'm going through different types of agents, by the way, because we have different types of agents that work together in terms of even the human thinking. And our problem solution is going to be a combination of many agents. So here's the right thing, the rational agent. So the rational agent maximizes the expected value of the performance measure given the percept sequence to date. So rational might equal best or might equal optimal. So yes, the best is of its knowledge, or best of its abilities, including any constraints. We all get this in many different things. If you think about the concept of managing your budget, you have a rational agent that says, I should pay the rent before I pay this over here, or before I pay that over there. Sometimes we call them priorities. Well, that's our rationalization. That says, before I spend money on this, I have to make sure I have money left over for that. If you're rationally thinking about that. Well, some Americans don't rationally think about money, though. It's not a rational concept. So behavior and performance of AI. So we have the perception or the percepts, which is the sequence. This is where the action mapping comes into place. So we come up with a map for the perception, which is a flow chart of the sequence of events that's going to occur. We have ideal mapping, which specifies the actions an agent ought to take at any one moment in time. So if it's raining, put the windshield wipers on. If it stops raining, stop the windshield wipers. So it's a map of the particular events in the sequence, along with a description perhaps for a lookup table, or maybe also, the data might be in a lookup table, it might be a closed form, it might be a flow chart. It might come in different forms depending upon what it's going to be used for. And then we have the performance measure, which is subjective. So you measure to characterize how successful the agent is. If the agent is successful, then you keep it going. Otherwise, you make it learn, or you modify the agent behavior to make it more successful. So speed, power, usage, accuracy, money might all be associated with that. And then the degree of autonomy, which basically is to what extent is the agent able to make decisions and actions on its own? And how effective is it? If it can't make the actions on its own and it needs too much human interaction, then you need to automate it a little bit more, if possible, basically in concept. So how's the agent different from other software? So agents are autonomous. So they act on behalf of the user. So the first thing that comes to mind is like when you're developing agent solutions, you're wondering, okay, so how do I know if this is an agent? And how do I know how to divide out the software program into different agents? So that's why I say the intelligent agent of the information agent that we get is acting on your behalf. So you go to Google, you ask Google for cameras, or you ask it for the title of this book that you're using for this course, and it comes back and tells you where to get it from. So it's acting on your behalf, performing work for you, instead of you performing work for it. So it's not like the data entry, word processing. Spell correcting is an agent, actually. Spell checkers are agents. They're checking and correcting stuff for you. They're doing stuff for you. Agents contain some level of intelligence, hopefully. They're making decisions. They're applying human learning. And it's not necessarily find this, find that. So a query from a database is not intelligent. An SQL query that goes out and finds all of the people with the first name Bob, not so intelligent. It's automation. So it's allowing you to search a database for a solution. It's not acting intelligently by definition. We have agents that don't act that don't only act reactively, but sometimes proactively. Those would be agents for indicators, for status. As an example, you see them all the time, like little smoke detectors. Sometimes they actually change color. The light will change color when the battery is running low, or it will blink to tell you, hey, you need to change my battery. Or you see sensors that go, as an example, traffic light signals are somewhat intelligent because they're telling you, instead of an on or an off, go or don't go, they're telling you, okay, maybe wait a few minutes. We have yellow in there. So it's helping you act a little bit proactively. It says if you see yellow, you're supposed to slow down because you can still go through it. But you're supposed to know as an indication that, hey, it's going to be red any minute now. So you might want to think about it being red. So agents will act reactively or proactively. And they can also have social ability. So that is, they can communicate with the user, the system, and other agents as well. Siri's very social. She has the ability to communicate through natural language processing back to the human and treat the human with respect and with all the personality traits that the human likes to be treated with. Agents also may also cooperate with other agents and carry out complex tasks together. So Siri actually communicates with information agents that find information. So she's the intelligent agent that's providing the natural language processing, and then we have the agent that's actually doing the search for the information, that's finding the data, it's delivering it back to her so she can deliver it. She's not doing all the work. It's broken out into multiple agents. And then the agents may also migrate from one system to another. They might move. Actually, the best form of an agent that actually migrates from one system to another and uses remote resources or even meets other agents is the virus. So every one of their computer viruses that hops from server to server is a virus by definition is, well, it is intelligent and it is an agent. So it's a reactive agent though. What it does is it goes in and it reacts with the data that it finds, and it sends out, for example, viruses that go, or agents that hop from server to server, collect information and send it back somewhere. They're doing work for the human, the virus creator, who says, go give me everybody's personal information. Okay, he goes out and gets it. Or go out there and destroy everybody's hard drives. Okay. It works on behalf of, so technically it is an agent, actually. Not a good agent, but it is an agent. So we have the environment that we have to identify. And this is what's referred to as the environment map and environment characteristics. So one of the assignments is going to say map out the environment. Here's how you would do it. This is slide number 29 of lecture number 2. So in terms of your environment types, you have different characteristics, and this is how they're measured. Accessibility versus inaccessible. Is the environment, in terms of its quality, is it accessible or is it inaccessible? It means, can you get there, can you not get there, depending upon, or can you find or can you not find? Does it exist, does it not exist, is it imaginary, is it physical? Is it deterministic or not deterministic? Can we tell what it is? Do we know ahead of time what it is? If it's an outside environment, it might not be deterministic. As an example, you have a robot, and the robot has wheels. And you have a non-deterministic environment when you can send the robot anywhere. So how do you know if it's on dirt, or it's on sand, or it's in water? That would be non-deterministic. If you know that the robot's only going to work on a track, it's determinable. We know what the environment's going to be. It's going to be a track, which is basically going to be accessible as well. It might be inaccessible if we don't know if the robot's going to be there or whether or not that environment's going to exist. Episodic or non-episodic, well, it means is it going to happen in particular contexts of a scenario, of an episode that's going to exist? Meaning, is it going to be related to stock prices? When the stock prices falls, the intelligent agent's going to come out there and it's going to say, hey, you know what, this happened, so we're reacting now. We're going to do something about this. Or, in the case of an emergency, the user slams on their brake. That would be an episodic. Brake controls, automatic, what do they call, hydraulic brakes and all of the anti-lock brake, those are episodic. Happens when the user steps on the brakes. Doesn't happen any other time. You hardly even know you have a braking system. So, hostile or friendly, is it going to be working with other agents or other humans all the time, or is it only coming up to solve a problem? Is it going to hit a negative? Is it going to hit a positive environment? Is it going to be reactive in terms of something bad or something good? Like a triage kind of agent. Static or dynamic, is it always constantly going to be changing, or is it going to be fixed in terms of certain scenarios? And discrete versus continuous. Search engines for, the information retrieval on the internet is discrete. We don't always run a search engine constantly, but our human thinking is continuous until we stop thinking, and then we are sleeping. We even think when we're sleeping too. So we're continuous. Our environment in our human head is continuous. So here's the environment types, and they're mapped out. And here's some examples of different environments. As an example, operating systems, Mars, office environment, virtual reality can be mapped out. And the environment types are largely determined by the agent design. So the agent design is going to be made for each one of the environments. And so episodic operating systems, no, they're not very episodic. They're not very static. They're very dynamic. Discrete, yeah. Deterministic, yeah. Accessible, yeah. Office environment, accessible, not always, not always, not always, not always, not always, for everything. Mars, semi. So the semi in here is basically saying it could be yes, could be no, could be sometimes. So the way that you describe the environment is going to be based upon the criteria that you're picking. These are main categories of environmental factors. So the structure of the intelligent agent. So it's the agent which equals the architecture plus the program. The architecture is going to be the hardware or the foundation it's going to work with. Agent programs are implemented using the percept action mapping. And the percept action mapping is going to give us our reactions. So when we are a robot that's supposed to go over a rock, then we're going to, apply more pressure so the wheels go up because we hit a rock. Or we hit a wall, we're going to back up. Or some other scenario happens. So it's a reactive model. The functions here's the skeleton of what I'd call a reactive model that you can put together. And the function might be a skeleton agent here for returns an action, memory, update the memory, perform an action, update the memory, because we have to keep track of what's going on. So we can keep track in terms of storing variables or storing data that's associated with each one of the actions. In terms of the architecture, that's the device that can execute the agent program. The mobile phone might be the architecture. The robot might be the architecture. The computer program, general purpose program, specialized devices, things of that nature. So we can use what's called a lookup table to encode the mapping agent response action. So here's an example of the collision avoidance. We have sensors. We have 3 proximity sensors as an example. We have some effectors, the steering wheel, the brakes. So the question might be how to generate the information, how large, how to select the actions. So if we're looking at this picture here, and you can you can see it better than I can because you can just see the lightness here. So these are basically going to tell us where there's stuff. We're trying to avoid collisions. And in our map of our environment, we're going to see from this image that we've obtained, we're going to see this information. Well, this happens to be the sun. We're never going to hit the sun, really. I've never heard never car actually run into the sun. So, but they could run into a person, and we see a lot of people here. Then we see this over here. Well, that's the stadium, not even on the track. So what we can do is narrow it for the obstacles. So from the sensor, from the agent position, we can see obstacles at different locations. And then what we can do is apply a general formula to approximate. And we can come up with a table of all of these things and figure out, well, when in relationship, this would be part of our mapping, our lookup table for our mapping. In the relationship of our map and our environment, the sun is unattainable. We can't hit the sun. We don't have to worry about that. We can slash that out. The stadium, the bleachers, probably not either. Anything on the track. So we narrow it down, and so we can adjust the sensors. And so we can make the table big, we can make it small, and just include the pertinent information. And then we have to decide, well, how are we going to select an action from this? Well, we're certainly not going to be worried about the sun. We're certainly not going to be worried about the bleachers. So in our problem solution, and this is what I call the pre-planning stage, or the planning of the problem, is to determine how you're going to generate each one of the obstacles and how you're going to use it, represent that knowledge in form of a table or in form of a data structure somehow. So we have different agent types, and this is also going to be something that you're going to need to know, and it's page number 35, slide 35 of lecture 2. You're going to use this as a resource for one of your in-class exercises. we have reflex agents with internal states, goal-based agents, and utility-based agents. We also have other types of agents as well, but what I'm going to do is sort of diagram out to you the different agent types. So we always have the environment, we always have the agent. So this is the big box here is the agent, the box over here is the environment. This is how they all differ. We always have sensors and we always have effectors. If you remember, those are the criteria that we're defining the agent with. So we define the agent by this information. So we say the sensors are coming from the environment, the effectors are going out to the environment, and we can define the environment as a separate component. We just did a few minutes ago. But for the agent behavior, we have what the world is like now, and what action should I do if it's a reflex. So the condition is the action rules. So if it's raining and I'm a reflex agent, I'm going to turn on my windshield wipers. If I stub my toe against a wall and I'm a human, I'm probably going to start tearing up or yelling or screaming or reacting some form of reflex that's going to occur that's going to trigger some emotion of, oh, I just hurt myself, I just stubbed my toe or something, which is a reflex. So this human behavior in terms of reflex mimics quite nicely to computer agents. It's the reaction, but it's programmed. Believe it or not, we're programmed too. So, because you see this funny, when you see kids, they fall down, and it takes them a few minutes to realize that they fell down, and then they have to decide, well, then they have this confused look on their face like, what am I supposed to do now? And then they decide, I'm supposed to cry. And they start crying for no apparent reason. It's like, well, you don't cry just because, then you have other kids that, just say, okay, if you don't, and then they start crying before you finish your sentence because they're too quick. They go, I know she's going to say something negative. She's going to take something away. So in that particular case, I'm going to react now. That's a reflex. We learned the reflex. So the intelligent agent on the computer learns the reflex too. And then they figure out, oh, that's how we're supposed to respond. So that's how Siri comes back with, it knows whether or not you're giving it a serious question, and she knows whether or not you're giving her a funny question. Like, Siri, will you marry me? It will come, ask Siri. And then, actually, I think if it doesn't sense the gender. It does not sense the gender, I don't believe. I haven't played around with this yet because I actually don't have the phone yet. But I've heard like so many YouTube videos where it's testing to see can it tell if you're a male or female, because it should come back with a different response depending upon that, if she thinks she's female. And then it comes back with, does it know what state you're in? Does it know if it's night or day? It doesn't, So it's like trying to figure out how intelligent is Siri. But if you ask her a stupid question like, Siri, are you hungry? She'll come back and she'll say something to everything. So, tell me a joke. That's easy, actually, but that's the one they use in the commercials. But actually, the radio commercials really love that because they go, what's the best, give me all the best hits, or something like that. And it comes back, here are the best, I found the best hits. And then it comes back, well, what radio station are we on? 98, then it tells you the radio station. So, anyway, kind of makes fun of Siri's intelligence, actually. So those are the reflex agents. Learning that you're supposed to cry when you hurt yourself. And that's how the agent actually responds by a condition. Reactive agents. This is the, if you do that, well, no, I'm not going to do that. This is the learned cognitive behavior of negative and positive reinforcement for reactions that humans learn through negative and positive reinforcement. If I'm good, then I'm going to get something. So then I'm going to be rewarded. And if I do something bad, which is in reaction, so we treat our intelligent agents on the computer the same way. So agents do not have internal symbolic models like humans do. Humans have values and morals and models, and we react accordingly to that. So we get offended or we don't get offended. But intelligent agents don't normally have that on a computer. So you can act by stimulus response to current events. That means reactive to. So the reflex and the reactive are very similar in terms of what happens. Reflex is supposed to be automatic. Reactive is supposed to be towards a trained, conditioned environmental factor. Each reactive agent is simple and interacts with others in a basic way. So complex patterns of behavior emerge from the interaction. Benefits: robust, fast response, challenges, scalability. How intelligent is the reaction? Is it kind of like input-output? And how are you going to debug them? So here's an example here. Agents, reflex, reactive agents with state. Sensor comes in, it says, what's the state? How the world evolves, what are my actions, what my actions are going to do in terms of looking at, what if I do this, what if I do that? So when we react, we normally think ahead. It says, if I pick up the dollar bill that's on the floor, if I'm a reactive agent, if I put it in my pocket, because we already know about all the scenarios, well, so does the agent, because you programmed it. It says, if I pick it up and put it in my pocket, someone's going to think I'm stealing it. But if there's a person standing there, then I should ask the person, hey, did you drop the dollar? And then you're supposed to go through. That's what you're programming in. So the big question when you do that is, how intelligent is this? And you think about it, how intelligent are we? Just because we learned we're supposed to ask people, does that make us honest, in terms of a characteristic? Or are we just following reactive behavior that we've learned? Like, as an example, when you hit somebody in an automobile, you're supposed to pull over. You don't pull over, you get in trouble. So are we pulling over because we're concerned about the person? No. We're pulling over because that's what we're supposed to be doing. If we read the driver's handbook, we're supposed to pull over. So, but some people don't know that because they don't read the driver's handbook. So, action is conditioned with rules. So rule-based reactions exist. Then we have goal-based agents. Some of you have a goal. You want to get a graduate degree, and then you want to get a good job. Everyone in here probably wants a good job. I would hope so. I would hope to think that you were going to get a good job. So you're an agent that's responding to the goal with the goal in mind. So every activity that you're going to do, hopefully, is going to lead you closer to the goal, because you're goal-based normally. So some of you may not be goal-based, but we look at the state and we look at the goal and we compare the actions that we can take with the potential distance and the decrease in the distance between where we are now and where we want to be, and we see which one is going to lead us closest to the goal, which is how people don't act rationally. Because they think, if my goal is to get rich, then they'll take a route, and they'll decide to take a route, like robbing a bank as an example, because it seems to work, and it's going to lead me towards the goal, but it's irrational. Because if they thought about all of the other rational parts of robbing a bank and what could happen as a consequence, they're not reactive, they're not reflective, they're goal-based, 100%, which, more power to them. But you have to combine multiple agents together, which is why we're complex as humans, because we have multiple different types of agents that are working with us. It says, well, our rational agent that's not goal-based is going to tell us as a reflex, oh, we're going to get caught. I mean, most people think, well, you're going to rob a bank. Well, you're going to get caught. It's the first thing you're going to think of, instead of, we're going to get rich and retire and move to Hawaii. So it doesn't necessarily work that way, but some people don't have rational thinking, so the rationality doesn't kick in. So anyway, psychologists have a lot of fun with that, actually, because then they can go, well, it's your rational agent. And psychologists use the agent terminology as well, because it defines human psychology. So this is where artificial intelligence for computers overlaps into psychology a little bit. Some of the terminology is the same. Rational-based agents versus irrational. So goals towards a goal, regardless of how you're right and wrong to get there. Utility. I'm a student. So as a student, I'm going to buy a computer. And I'm going to think, when I buy this computer, what computer am I going to get? Your agent's going to tell you you're going to get something that's going to work for your schoolwork, because that's what you're buying it for. That's the utility of the computer. I'm going to get a car. Well, I have 3 kids. Am I going to buy a roadster? Convertible roadster? Sure. No, it's not the utility of it. It's going to be like a bigger car with more seats in it. Or, I want to... Anyway, the utility looks at how we're going to use it, how it's going to fit into the goal of the big purpose. So how happy am I going to be in a particular state once I buy it? Yeah? Doesn't have to be. You can have utility without goal. Antivirus software is utility-based. It looks at the likelihood of something causing a problem, then it weighs it and says, this is a potential risk. Do you want to do it? And it lets the user decide, well, I want to go to this website. Yes, I'm going to violate the utility. And then the utility agent, though, is looking at this going, well, in the big picture of the schemes, this website is a problem. You shouldn't be going to this website. A goal is going from point A to point B in the fastest amount of time, so all decisions are based on the distance left between point A and point B, given the route you're taking. So if you're in a car and the goal is to get there as fast as possible, you're going to decide on a different street. And you see a bunch of cars over here. If the utility is to drive, you don't care about getting to your destination. Your utility is just to be in the car and drive, and you're doing that. So you could be stopped or you could be running if the utility works. If you're goal-based, you're going to make decisions according to how you're going to get there in hopefully the most optimal way. Otherwise, you're never going to make it there, because the reason why you exist as an agent is to get there. Versus the utility of an antivirus program is to keep viruses off your system. The utility of a student is to take classes, and your goal might be to graduate, so you'll take certain sequences, but your utility is to show up here at 9 o'clock in the morning. Because if you don't, well, it's both a utility and a goal, but in order to be a student, you actually have to be a student. So the utility is to actually be a student. So in terms of the concept, but you're looking at the state, you're looking at how the world's going to evolve, you're looking at what actions am I going to do, and the criteria is the utility. Is this going to make me happy? Is this going to be counterproductive to my utility? I'm a student, so if I take the next 6 months off and go to Hawaii, is that really being a student? Well, unless you take online classes, then that would be a student. So your utility would still be, your function, you have utility in terms of the goal. Then we have mobile agents. Mobile agents are not agents found on mobile phones. Mobile agents are agents that move from one location to another location. The agent itself is mobile. So the agent rotates around the world. If Siri were to be incorporated into, and I think this is probably going to be the future of Siri, into a car, that would be mobile. If she jumped from your phone into your dash of your car and then gave you directions, that would be really cool, actually. That would be like, okay, Siri, take me to school. And then you get in your car, and she comes on, she gets on your radio system. She's okay, Barbara, I'm taking you to school right now. Okay, and then the car actually just drives itself at this point, probably in time. But that would be a mobile agent, because it jumped from this device, from this platform, to that platform over there, and went from, and that makes it mobile. It's the agent that's mobile, not the device. Keep that in mind. So programs that can migrate from one machine to another, execute in a platform-independent environment. It's kind of like the futuristic, was it The Matrix or something? Or I can't remember what movie that was, when the thing just followed them around. No, actually, it's the Verizon network. I don't know. Follows you around. I don't know. No, that's a bad example. It's, actually, when you get your email on your email agents, when you get your email on your phone, you get them on your computer, you get them on your tablet, you get them on your watch. That's mobile agent behavior. It's an email client. Is it intelligent? Not necessarily, but it's mobile and it's an agent. So we have agents that are agents, and then we have agents that are intelligent. So you have to make sure you put the intelligent agent if you're going to describe it that way in terms of an AI solution. And I know I'm running close on time. So mobile agents are going to be, just 5 more minutes here, we'll be ready. Not necessarily for sufficient condition or agenthood. Their mobility may not be for that purpose. They're practical, not non-functional advantages, so they reduce communication costs. So you don't have to send, and when it says reduce communication costs, one agent doesn't have to communicate with another agent. It's the same agent. Because the problem is, like, you have this here. You told Siri you want to go to school, but you get into the car, and are you going to use the phone as your navigation device, or are you going to use the car as the navigation device? So an agent that could communicate is going to send data back and forth. That's going to make it slower. So you can reduce the costs and make it more efficient by having that agent jump from this device to this device here. Kind of like the way your email jumps from your computer to your phone to your tablet. So practical, 2 types of agents. One-hop mobile agents that migrate from one place to another place, or multiple hops that roam the network from place to place. That's the virus. the virus agent is a mobile agent because it goes from one computer to another. If it didn't do that, if it didn't do multiple hops, it really wouldn't be a good virus. And the purpose of the virus is to spread throughout the entire network as fast as possible. So that is basically good. Some applications of this: distributed information retrieval. Your information retrieval AI search engine agents are multiple mobile agents. And telecommunications network routing. Routing systems have mobile agents inside of them that determine different routes. So what I'm going to do, oops, I didn't want to do that. Hold on one second. I have 2 more slides left. And then what I'm going to do is break off for lunch. And then at that point, we are going to come back and do the first exercise. So I'm sorry, I accidentally hit the keys too many times. So we looked at the different types of agents, and now what we're doing here at the end is looking at information agents, and this is the search engine, the last type of agent I forgot to cover here. Manages explosive growth of information. So the information agent or the search agent that's part of your Google or your Yahoo is the key to information retrieval on the internet for most people. In fact, even what is that other one that we have now? It's Bing or something. It's nothing more than an information agent with more intelligence. Perhaps. I've never used Bing, actually, but I probably should check it out. Did anyone here use Bing? Is it better than Yahoo or Google? Does it do the same thing? Oh. It's better? I don't use Yahoo. I'm a Google person, because I don't know. But anyway, long story short, they're all supposed to be doing the same thing, but they're doing it differently, and one of them is supposed to be better than the other, because why would we have multiples if one wasn't better than the other? The thing is that they're thinking differently about their intelligence. In the old days, one used to be for education, and we had more of them out. Actually, we still have more of them out there. But it was for retrieving commercial versus retrieving educational institutions versus research and so they were all specialized in different categories of what they were trying to do. So manipulates and collates information from many distributed sources, and the information agents can be mobile or static. And here's some examples: bargain finders, Fido, internet, softbots, different programs to get certain things out. So challenges might be understanding the internet, might actually be annotating web pages and finding the information. So there's different ways of optimizing the search engines, optimizing the information that's on the pages, and we know about metadata for anyone who's done web development. So you put that in a web page, and then it shows up, and you get higher search results that come out of that. So it's a game, actually. So once you understand the agent, then you can build your application to work with the agent, and then you can build your website to work with the agent so you can get a higher hit ratio. So it makes it more findable for the agent in the end. Okay, so in summary for our morning session, we looked at the concept of intelligent agents in this second lecture. So anything that can be viewed as perceiving its environment through its sensors and acting upon the environment through its effectors, and maximizing progress towards a goal is the definition of an intelligent agent. Agents come in different types, as we've seen so far, and these are all intelligent agents. There's a reflective, reactive, we have information agents, we have all sorts of utility, goal-based agents, all sorts of different types of these agents. We can define the agent behavior in terms of a page with percepts, actions, goals, and environments. We can define the environment in terms of those characteristics I gave you before: discrete, not discrete. Is it findable, accessible, inaccessible? All those different criteria. And there's different criteria that you can add to change your environment, because environment is kind of a general concept. You have to add your criteria to define your environment so you can design your agent to work in that environment, because agent behavior is very environment dependent. And we can use a lookup table or a closed form or some sort of an algorithmic approach to deciding how the agents are going to work with each other, which is our underlying algorithm that we're going to use. And here's our agent types: reflective, state-based, goal-based, utility-based, reactive-based, and reflect-based are pretty much the same, reflex-based. And then we have this concept of the rational agent. So that's the action that maximizes the expected value of the performance given the percept of the sequence to date. So rationality as it relates to agent behavior is making it so that we're doing the right thing to go to the goal of the agent, whether it be utility, whether it be goal-based, whether it be information-based. So, and that's actually the rational thinking in any decision that we make. So just think about rationality in terms of human logic and human thinking. The rational choice is going to lead us closer to whatever our agent behavior is supposed to be doing. The irrational choice is leading us astray, causing more problems for us. So, all right. So let me end this video.